Well, the way I've designed this tutorial to work is that we're going to build a machine setup from scratch, including some solid models to enhance simulation. And then we're going to use that machine setup on a couple of different Swiss projects. One project is going to be doing a very long part, which will require a number of rechucking procedures. And then the second part is going to be doing some live tooling. Let's first take a look at the machine that we're going to try to, we're going to build. And I'll pull up the kind of a diagram of the axes we're going to identify. And you'll see that in this particular machine we have what I would call a main gang turret that has 6 turning stations. It has 4 live tooling stations here, and then it also has another 5 stations that are fixed stations mounted to work on either end of the part. Now this particular turret, as we'll call it, or gang turret, can move in 2 directions. It can move along the y-axis and it can move along the x-axis. Next thing we have the Sub Spindle. The Sub Spindle, listed as C2. Sub Spindle is mounted on this, we'll call it a turret as well, which happens to have 2 live stations, 21 and 22, and 1 fixed station. Those tools, of course, can be used on the end of the part, much like these tools here could be used as well. Next, we have another tool station, an end working station. These tools would be used to work on the end while the part is in the sub spindle. And you see that we have 3 stations that are rotating live tools, and station 31 is a fixed station. You'll also notice that the axes for Z moves this way. So positive is moving out this direction, negative is moving in this direction. And you'll also see that this end workstation, this end station, has another axis, an X3 axis that moves up and down this way. So we can do some motion along with the axis here. So we're going to take and we're going to build this machine setup from scratch. Now there's a number of ways you can do this. You could do this out of the box in a spree without doing any type of solid models. You can actually define all of these components without building a solid model, and we'll talk about how to do that. However, we are going to take advantage of some solid models. So when we get to the point of actually using those solid models in our machine setup, I'll explain what you would do if you didn't have those. So it'll make sense to you what to do if you don't want to take the time to build those solid models. However, I do strongly recommend that you consider doing that to enhance your simulation. So we'll move this out of the way, and let's now open up a file. So we'll go up to File, Open, and we're going to look in your Esprit Tutorials files. And as long as when you inserted the CD, as long as you hit the Install Files button, step number 1 in your tutorial, it would have created a folder under Esprit Tutorial Files called Swiss Turning. And under Swiss Turning, we're going to have a list of files we're going to work with. We're going to start with this first file. Number 1 is a Swiss machine setup. We're going to open that up. Now when we open that up, you really don't see anything going on. It's just the machine setup is in here, and there's really nothing exciting to look at. And in fact, if I were to go in, it is in turning, if I were to go into common machining and machine setup, what you'll see is that it's a standard turning machine setup, in that it's a stock out-of-the-box turning setup. If I go to assembly, you see there's a machine base, 1 index turret, a main spindle, and a tailstock. And if I look underneath any of the components, if I look under the index turret, it is an index turret. It has an axis that indexes the turret, so it's a traditional turret lathe. It has 6 stations. You'll see that we have a main spindle and we have a tailstock. So clearly we don't have enough information here. And if I go to the NC output page, this is set up to post by turret. There's no information about heads or anything of that nature or synchronization that's listed. Those are things that we're going to add ourselves. Now this file is not completely blank. There are other components in this file. They just happen to be on some other layers. So I'm going to open up my layers list, and we have a number of layers predefined on this particular file. If we start with the main gang, I'm going to open that up. You'll see that I've already constructed a solid model of this main gang. And in fact, if I get, we also have some views here. If I go into a work plane or a view plane for the main, so look into the part this way, you'll see that we have also some dimensions thrown up here so we understand the dimensions of how the tools are to be laid out on the part. Now, if we take a look, again, this solid model is something that I have modified a bit. I'll admit I borrowed this from another machine setup, and I just have kind of modified it to suit my needs. But it is a solid model. It's not an STL file. It is a solid, because one of the things we're going to do is we are going to make it suitable for making a solid out of this. So this is designed to kind of try to match this picture here for this main turret, this main gang. So it's on this main gang layer. The next component we'll mention is the sub. I have a sub listed here. If I roll this thing around so we can take a look at the other side, you'll see it has the sub and, I'll turn this on, I can see it a little easier, the sub and the 3 stations attached to it. Again, 2 of which, as you recall, 2 of which of those stations are live, and the 3rd station is a fixed station. The next component to look up is one called T31 through 34. That's this end working station. I'll roll it around this way. That's the end working station that matches up here with these tools across like this. So the first station that you see listed there is, this first station is a fixed station, and the other stations are rotating stations. Now you'll notice that on each of these, if I change this so I can see it, on each of these solids, I have laid out some dimensions so that we know these dimensions. Now this is important because we need to know the distance between these stations, because it's not enough just to have the solid model there, but we must also tell the machine setup how far between stations each of the tools are going to be located at. So it's important. You'll also notice the positioning of these solids. For example, this solid is setting so that X0, Y0, the origin, I'll just say it that way, the origin, we'll talk about the axes in a moment, but the origin is in the middle of this first station. And if I look at the sub spindle, you'll see that the origin is sitting in the middle of that station, of the sub spindle, sitting right in the middle of the sub spindle. And if I turn on the main gang, you'll see that the origin is sitting at the locating area, this locating face, of the station number 1, the very first station that goes in, the first tool that will go in. That's where it's located at, and that's where the X0, Y0 would be located. So if I turn all of these on, it's going to look a little bit cluttered because they're all going to be kind of sitting on top of each other. But this is important. It's setting this way for a reason, and that reason is that when we actually define these as axes, as machine setups with axes, when we use these components in the machine setup, it will have a point of reference to move from. And so it will know that when it goes to X0, Z0, it knows that the main spindle of this is going to be on center line. So it's important to have that point of reference. So you don't just simply put an STL file or a model up there and just kind of haphazardly put it on the screen. It's important that you locate it such that the machine setup will understand and use it properly. Now the next thing to take into consideration is the axes themselves. If I change back to my work plane of XYZ, and you see I created some other work planes, and they're really more for convenience than anything. If I go to the sub spindle, I'm looking into the sub spindle. If I go to sub spindle end, sub end, I'm looking in the end of the sub spindle. Or if I go to the main end, I'm looking at the end of the main gang. But if I go to XYZ, and I'll roll this to an isometric, kind of an isometric view here, like so. If I now turn on my axes indicators, if I do a right-click, view, get out here on the screen a little easier so you can see, right-click, view, and UVW axis, you'll see how the axes are laid out. They're really not laid out the way you might think they should be. For example, if I'm in turning, if I'm normal turning, pretty much everything is set in this orientation in the XYZ work plane. If I can get a top view, it's this view right here. But you see how these solids are not laid out in this orientation, nor are they laid out in an orientation that really makes a lot of sense other than to the axes of the machine. And you see how the Z is pointing in this direction, the X is pointing in this direction. Now if we look at that from, let's say, the end of the part, let's see what we get here from a view that we might want. This main end view here. This is really the view if I'm sitting as an operator looking in the door at this machine. Now the only thing that's a little different about this is if we look at the axes, we look at our picture, we see that this is a Z, and this Z is actually going positive in this direction, and this Z is going negative in this direction. Well, what we'll do is we'll actually tell that information in the machine setup when we'll tell it the direction of Z there. But we're going to leave it in this orientation because we want the X and the Y values to be correct relative to the normal orientation of the machine. So as it sits on the machine right now, this axis here is going to be Z. Here's my X going up and down this way. And then, of course, my Y-axis will be going across this way. Now, once I have these components created, and again, I'm not going to go through the process of drawing all these things from scratch. We cover the way to use the solid modeler, which is found over here under Create Solid Modeler. We cover that in other tutorials. We cover that in the beginning tutorial. We also do a little bit of that in the advanced milling and the advanced mill-turn tutorial as well. So these are already predefined and created as solids. Now, one of the things I need, if I'm going to use these in my machine setup, is I am going to need to use to actually create what we call Stl files. That's what we actually use in machine setup. So what I'm going to do is actually group one of the solids. Now, if you have multiple solids on the screen, that's fine. Just whichever one you group is the one that you'll be able to create an Stl file for. And while I have this grouped, I'm going to go in and create save this off as an STL. Now, the process I'm using right now requires you to have the Stl Data Translator. As I mentioned before, it's not necessary to have these solid models. However, there is a keen advantage, and you'll see as we use this machine, in having these. Now, if you do not have the Stl Translator in your Esprit license, then certainly you could use any other CAD product to create these Stl files. Only thing I caution you about is I would first bring those solid models into Esprit and position them in the right location with regards to the axes and the origin, and then maybe pass this file back to your CAD software as a Parasolid or AXIS file. And then in your CAD software, you could then construct the STL files. But you don't want to just throw STL files out in space somewhere. The machine setup really is not really configured to try to find those locations. It's best to prepare these up front like I've done here. So I've grouped my main gang, and I'm now going to go up to File and Save As. Now again, keep in mind that I'm doing that because I have the Stl Data Translator on my Esprit license. And what I'm going to do is I'm going to drop down to Save As Type, and I'm going to tell it I want to create an STL. Now, one other thing, consideration to look at is under Options. I'm also going to look under STL, and if I want to, I can adjust the tolerance. This is one thing that gets a lot of people in trouble, is that if they go to the trouble of building a real complex solid model of a component for their machine, say they add a bunch of screws or some text, some engraving, or some whatever fancy things you want, coolant nozzles, whatever you wanted to add, you can clearly model those things on here. But it's kind of it can kind of bite you a little bit if you make some really fancy solid, and then when you start running a spree with that solid, you start finding some performance issues. And so one way to help reduce some of those performance issues is that you can go into the Options page, and you can change this tolerance to something else. Let's say I change this tolerance to, let's say, 50 thousandths. And what that will do is it will create my STL file with a higher tolerance and make the file much smaller. And that will help improve your performance. And of course, this is something that if you're doing this in an external CAD system, if you're doing this in some other CAD system, you'll have to use their technique to change the tolerance to reduce that. Esprit, when it uses these STL files in the simulation, in the machine setup, it does not have any way of filtering or making this file smaller. It's going to use the file as it was constructed. So any decisions about increasing tolerance for performance need to be made at the time of creating the STL file. So I've set my tolerance. I've hit OK. And now I'll give it a name. I'll call this will be my my main gang turret. And I'll hit save. When I do, it creates a STL file. Now I'm going to save this next one. I'll group it. By the way, if you don't group anything and you go up to do a file, save as, in Esprit at least, and if I say STL file, and I now give this a name, I'll call this my Sub Spindle. If I hit save, it's going to give me a warning. It says more than one valid element to save. Please select the element to export. So I did not identify which solid to do this with. So you have to make sure you pick a solid first. Then you can go in and save as and use your STL. So under STL, now the option should still be set to 50 thousandths, and it is. So I'm now going to give this a name. I'll call this my Sub Spindle Turret. That's what I'll call it. And I'll go save. Now I'm going to go ahead and pick the next solid here. And I'm going to go in and save it. File, save as, STL. And we'll give this a name. This will be the end working turret. Oops, give it a name. Oops, my fault. Let me change that back to STL, and let me pick the right field first. Kind of silly me. End working turret. There we go. So save that one. Now I do have some other components here, and I'll just turn these off. And I'm going to now turn on, I've got a main spindle base, a sleeve, a spindle sleeve, and then I have our guide bushing. The guide bushing, we'll talk more about the guide bushing a little later, but it's an important reference for you. Of course, any of the Swiss machines have a guide bushing. We'll talk about the purpose of the guide bushing a little later, but the point is it's best to have something graphic to try to illustrate that guide bushing, and I do that in this case. So we have three other solids we're going to add. So I'm going to add, first grab this one. And you see again where it's positioned. This is positioned where 0, 0. Let me get a end view here. Be a top view actually is what I want. There we go. If I look at it from this side, get the right view that I'm after. No, that's fine. This distance from here, this is be Z0 if you will on the machine. This distance back from here to here is how far it is from Z0 to this spindle face. Different machines, different values. The point is these solids are set up correctly with regards to that distance from Z0 to this locating face of the main spindle. So I'll select this solid. I'll do a file, save as. We'll tell it it's now going to be an STL file. And we'll call this will be the main spindle base. We'll give it that name. Call it a base. I'll pick the next solid here. I'll do a file, save as, and STL. Click on the name field. This will be the main spindle nose is what I'll call that. Let's fix that name. There we go. Spindle nose. Save that. And let's get the little, get this guy here, this solid inside. I'm using this as a bushing. We'll talk about the size of that bushing and how I've designed it that way. File, save as, and STL, and we'll call this is the guide bushing, and save. Now you will notice as I save this that there was an existing STL folder there. Those STL folders, that STL folder there has really the same exact files that I saved previously that I'm using in the files that are the completed portions of this. So even though we're going through this from scratch, these STL files have been saved in another place, and they're on your system as you install the Esprit files. So save this now, and now we're done. All right, I'll turn these back off. So now once I have those STLs saved, I'm now ready to start thinking about what I need to do in the machine setup and make the changes that are necessary. Now this page, I'm not going to get too worked up on this page because as you well know, in turning, this is going to change per part. So depending upon the part you have, you'll have a different size stock, a different length, a different part length, a different amount of stock in Z that's sticking out for to face off. So this page I'm not going to focus on much at all until we get into our actual projects. The purpose of this segment of the tutorial is really just to build our Swiss machine setup that has all of the stations that match up with our machine. So we want to match up with this machine with all of this information. So we're going to get started let's first take a look at this first index turret that we have listed here. Now when I select that index turret, you'll see the name of this turret is it just says Index Turret 1, and that's fine. There's nothing wrong with that name, except I'd really rather have something more descriptive. I'm going to call this the Main Gang Turret. Okay. The number is turret number 1. That's fine. The radial output is diametral. That's fine. Now turret style. This is an important choice here. Index would clearly be wrong. Index would be a traditional index turret lathe, and that's not going to work for us. Now we could use a gang turret, and that will work. And if you do use a gang turret, you'll now be able to go over to geometry, and under geometry you'll identify the physical dimensions of that gang turret. The turret size in X, which in this case would be the height, the turret size in Y, which would be the length, and the turret size in Z, which would be the thickness. And then the tool separation distance between stations. So however many stations that you identify, the size of this will change by this separation distance. Now the problem with that is, of course, what you'll end up with is just a block. You'll just end up with a single block, and that single block is really not going to help us much with this shape that we're going to be working with. It's really not going to be very helpful. I mean, we could define this as a particular turret, main turret, as one of these blocks. We could even attach this as part of that block as well, but we really wouldn't be able to put this on that same block because this type of gang turret that shows as a gang is really only going to be good for maybe these first 10 stations. We'd have to create a separate one here, and I really don't want to do that because this block is actually attached to this, so they float together. So really we want this all to be one unit, and which is what we've done in the solid model we have. So in this particular case, since we have a solid model, the choice of gang is really not appropriate. So what I'm going to do is I'm going to change this gang now to what's called a custom. Now of course I wouldn't use magazine either because that is for a tool changer. I'm going to use a custom. Now when I hit custom, you'll see how the geometry and configure stations disappears. That's because it's now going to use all the information that we plug in into the machine setup to customize this particular turret, including the graphics of that turret. Home position, we'll talk about that in a minute. Ensure tool station matches tool number. I'm going to do that. That way when I define a tool in a station, I make sure the tool number matches. That's a real handy tool in this case. I really like to use that on anything unless it's a magazine. A magazine is the only place where I won't do that. Any of the other adjustments I might make a move to tool change. I might adjust that to move X first, so it moves up in X. Right? The rest I'll leave alone. So now once I have done that, I can now move over and open up the main gang, and we can then talk about axes and tool stations. Axes I'll come back to in a minute. We'll talk about axes in a minute, but I'm going to start by going ahead and defining the tool stations that I want to define. Now currently, I'll close this axes for a moment. Currently there are 6 stations in this turret. And again, that's the default with the normal turret. But really what we're going to be using in this particular main gang that we have is we're actually be using 15. We have 15 stations here. So I'm going to go in and add those stations. So I'm going to go up and basically say new station and continue adding new stations until I get all the way to 15. Now, identifying those stations is only part of the battle. It's only a little piece of what we need to give the information wise. All that does is tell us that there are 15 stations. It just has nothing to do with where those 15 stations are located at. That I have to identify by going in and adjusting that inside of each station in these settings. I've got to identify those stations. Now the first thing I do need to deal with is when I go click on a station, you see how this angle changes? That's because these first 6 stations were defined as an index turret. I really don't want that. So one way to deal with that right now is in fact to go back to axes. I said we were going to skip axes, but we're going to come back to it for right now. We're going to hit this index and we're going to delete it. Hit delete. So now there is no index axis. So when I go to station 1, you won't see anything here because there's nothing to index. And in this particular case, there isn't. So that's going to all remain dimmed, so there's no value there. Now, in the station, a couple of decisions to make here. One is the position reference. Now, the position reference simply means where do you want to reference the location of the tool in the station? Now, you can use what's called the holder base. The holder base is being the end of the tool holder. If it's a turning tool, it's the end of the holder. You can also use the tool base. The tool base is like the end of it's right where the tool mates up with the holder. On a milling cutter or a drill, that's where the drill meets the flange of the holder, if there's a flange there. Tool point is at the tip of the tool. I'm going to use, on this particular turret, I'm going to use a tool point method. And I'm going to drive this from the tool point. And again, we may adjust this as necessary. Next, we have the axis. Now, one of the things we really want to do, we don't have any axes defined, so we'll leave it on default. And default is really the right answer. But if we had identified our axes, then you would have been given an option to change this. In fact, so that you see that, let's go ahead and do, in fact, add our axes. We've added our 15 stations. Let's now add our axes. So, under the axes, if we look at the machine again, we see that there's a y-axis and an x-axis. Now, the y-axis is very important because the y-axis is what moves this gang station and lines the tool up with centerline. And so if I'm doing any turning or grooving or a cutoff operation, those tools have to be aligned. Each of those stations have to be aligned with the center of my cut. The milling tools, of course, if I'm drilling on the OD, they too have to be aligned with the middle of the tool, middle of the spindle. So the y-axis is a very important axis in moving this into position. The x-axis, of course, simply moves this gang turret up and down this way, and that's the only axes of motion that turret has. So we're going to identify those two axes, y and x. Now, the order that you identify axes, when you define an axis with a turret or a spindle, it's important that the order becomes what we would call a hierarchy. By that I mean the order you identify the axes is the order of importance of the axes. So what I'm going to do is I'm going to identify first my y-axis, because clearly for any tool to work, y has to move to position that particular station relative to the part. So I'm going to simply grab y and hit new axis. Now, for a label, I could leave the label y, but really it would make more sense to label it like the axes show. I'm going to use y1 and x1 for my label. So I'm going to tell this as y1. I'm going to also tell it that the axes, I have the information here as far as the axis vector is going to move along y. That's what the 1 means here. And then we have a minimum maximum position. I'm going to tell it that it moves, let's say it can move minus an inch and it can move plus, let's say 20 inches. If you know the exact value, plug that in. Now, does that necessarily mean that's going to be a hard stop, like a stop in the machine? No. However, you can add logic to your post processor that can look at this number, and if you exceed these values, you can have it flag you in your code if you wish. But just understand that it's not a bad idea to go ahead and plug in the appropriate values here. Now, I'm going to plug in the next axis, which the next axis will show up underneath y1, meaning it will be the second most important axis on this turret. That'll be the x-axis. And I'll say new axis. There's my x. This is going to be x1. It is linear, and you see the 1 is in the x vector, which means it's going to move along x. And now that tool, we'll say that the minimum position in the minimum position, let's say, is minus a quarter of an inch. And let's say the maximum position is 12 inches. So I'm identifying the axes of motion. Now, after I've identified the axes, I can now start thinking about the tool stations and the locations of those tool positions relative to our turret itself, our gang turret. Now, of course, these stations aren't just sitting on top of each other. Each one is offset by a known distance relative to this solid model to position each of these stations in the correct position on the solid. As I mentioned, simply using a STL file or solid for this station does not tell each of these stations where to be located. You have to control that. You control that yourself by plugging in where those stations will in fact be located. So I'm going to go in and identify some of that information from from our graphics file. So I'm going to minimize this because there's no dimensions here, of course. I'll minimize this. I'm going to move this out of the way just a little bit over to here, and I'm going to go back in. Actually, let's hit OK real quick, and let's go back into our layers and let's turn on our main gang. And I'll go in and get a view. Let's look in top of it here, and I'll zoom in kind of closer, and I'll leave it like that. And when we open up machine setup, we should be able to see some of these dimensions. And we'll just kind of work our way back and forth from there. Now, one thing about that I will just point out here is it may be necessary to actually shift some of these dimensions both in X and in Y. Clearly, I'm going to be shifting some of these dimensions. Get that view again. Along this axis here, which is the X-axis in this plane. It's the X-axis this way. But I'll also have, which in this plane, but in the machine, of course, we're looking at that as being Y. That's my Y-axis. So we have that information to be plugged in from the Y. But we may also find some stations that need to be offset as well, off-center, to find those locations. So we've got it in position. We zoom it up again a little tighter so we can see. And let's now open back up our machine setup. And I'll move it out of the way a little bit so we can see both. Alright, so now we go to assembly, we go to the main gang, we go to our stations, and we click on station number 1, which will be this station right here. Now, under axes, you'll see now I have those axes. So I could identify a tool to move with an axis, but that's really not what we want to do. Really what happens is this entire gang turret moves with every tool. And so leaving this on default simply means it will move with the default axes of this gang turret. If I change this to something else, I'm telling it that this station can move independent of this main gang, which it doesn't. Now, if we look at the values here, I'm going to start with 0 here, and I'll say 0, 0, 0, which means I'm telling it that the location of this tool is going to be located right here at 0, 0, 0 for station 1. Now for station 2, and by the way, you wonder where that 7 inches comes from. You'll find that all 6 of these stations will have 7 inches on them. When I go to 7, I won't, and that's just because they were part of the original index turret. So those numbers were in there from that index turret. I'm simply editing those. So we're going to make sure that each of these stations is set to tool point, default, and we're going to plug in the appropriate location. So station 2, tool point, axis is default. Change this to 0, and now my Y will be a minus 886 thousandths. So minus 0.886. Okay. Now from here, I go on to station 3. 3, tool point, 0, 0 there. And now this one's going to be this 1.772. So I'll plug that in, minus 1.772. Now notice I put a minus there because it's in the minus direction of Y. If we look at our axes, here's Y plus going this direction, Y minus going this direction. So each of these stations is located along the Y minus direction. Go back to station 4 now. Tool point, 0. And station 4 here is 2.657. 2.657. Station 5, tool point, 0. And 3.543. Minus. Should have plugged in a minus there. Minus 3.543. Go to station 6. Change that to 0. Change this back to tool point. And now change this number to minus 4.429. And that gets all of those, drag it out of the way, that's all of the turning stations. Now I'm ready to move on to the next stations, and to do that I'll hit OK so I can move the screen. Okay, and I'm now going to drag this down, and now I'm ready to look at these next 4 stations here, which is stations 7 through stations 7, 8, 9, and 10. These are the live tooling stations. Now one dimension I see that's missing, so let's take a quick look, is you see how that station is actually off-center from 0. And so I'm going to need to know what that off-center is. And if I look, wireframe, there's no geometry here. So I'm going to go in and kind of construct some geometry. And I don't want to get geometry for the whole file. I don't know that that's really all that necessary, although it won't hurt. Let's take the whole solid. I'll do a right-click, copy. And under transformation type, I will say I'll do a smash. And I'll change it to a wireframe, and I'll set the tolerance to about 1,000th, and I'll hit OK. And that's going to get wireframe geometry now. Now I can go in and change my filter to geometry. I can pick one of these diameters here. And what I'm looking for is the center point. I'm looking for the center point of Z. And I see the center point of Z is minus 433. Minus 0.433. So knowing that, that's how far off center the center of that station is going to be. Now I'm going to roll it back around and go back to the front view of that station. I'll zoom in tight so we can see the dimensions here at the bottom, and we can also see the station. Now of course it's moving in the minus direction, and let's again go open up our machine setup, drag it out of the way a little bit. Go into assembly, main gang, tool stations. Now we're ready for station number 7. As you recall from the photo, station 7 is this first live tooling station. So station 7, again, I'll use instead of tool point, I'm going to have it use a different strategy. Instead of using the tool point, I'm going to have it use the holder base. That way the length of the tool will be reflected from a fixed location. In other words, if you look at these other, well, I can't really drag it over right now, but the turning stations, clearly you can slide those up and down in those stations to be really anywhere. And that's why I'm using tool point. But here, these stations, the tools are fixed. They're loaded in, and they only go in one location. Now, they can be different lengths sticking out, of course, but we can define that when we define the tool. So holder base is really a better choice for these live tooling stations. Now, tool position. So what we're going to do here is we're going to go in and plug in our 6.496, so it'll be minus 6.496. And then here we're going to make the shift in Z. And again, that's Z. It's offset in Z. And the direction I'm going to shift this in Z is minus 0.433. Okay, see how that works? Now I'll go to station 8. It's holder base. It's 0. It's going to be minus, get the right button there, minus 7.677. And again, minus 0.433. Station 9. Oh, one thing I better do. Go back to 7. I saw something here. See automatic tool changer? I want to turn that off. There's no tool changer with this station. So I'll turn that, make sure I'm turning that off as I proceed. So off there. Next one is 8.855. It's 8.858, excuse me. And then minus 0.433. And then we're ready to move on to station 10. Automatic tool changer is off. And the X will be minus 10.039. And Y will be minus 0.433. So now we have station 10, 9, 8, 7 defined. I'll hit my OK button. Now I'm ready to look at these next stations. Now these next stations are basically holes in this block, and we have the locations in Y, the Y to minus locations. But also there's another dimension here. Let me get the main end view. You see this dimension here, 4.638. That's the dimension from 0 back to the back end or locating end of this face. So I'll define the tools relative to that. Now you could, and probably I should have thought this through a little bit better. I might have rather done this from the middle of this base. In which case, why not do that? Because that way we can define the tool from the middle going in either direction. So let's determine what that's going to be. I'll do that by, if I find where, let's just go in and I'll create another quick dimension. I'm in this work plane, so I'll go up to dimensioning, and I'll dimension from here, from 0, point to the middle of this connection line here, and I'll place the dimension across there and across there. All right, and you'll see that it says 3.697. Move that dimension a little bit. There you go. 3.697 is what that is. So I know that dimension. What I'm doing right now is I'm writing that down. 3.697 because I have a short memory. Okay. So that's the distance we'll shift off center in Z for those tools. Okay, now, next thing we're going to do is I'll go ahead and get to a straight-on view here and zoom in so I can see those stations, like so, and we'll open up our machine setup again. Now keep in mind that what we're defining now are these stations 11 through 15. So we'll go into main gang turret, tool stations, starting with station number 11. 10 we did, and we're going to do 11. We're going to also use the holder base again, and what we'll do now is we'll change this, and we'll turn automatic tool changer off. We'll change this to the first line, which is 11 point minus 11.732. Now let's make sure we get the right station. If we look at our picture, here's 11 and 12 are here in this station. Okay, so we've got 11 and 12. And actually, it looks like I've modeled this thing. Yeah, it looks like I have. I've modeled this thing actually a little differently. I looked at the picture, but actually I've modeled it with 3 stations on this side, 2 on this side. Since I have the solid model created, we're going to go with this. So we're going to use this method. I just now noticed that. But anyway, 11.732. Now the Z will be minus that 3.697. Okay, see how that works? All right, now let's go to station 12. No automatic tool changer. So I'm making this one 11, 12, and 13, and then 14 and 15. So 12 is right here. All right. Oh, one other thing. Let's go back to 11. There's also is a dimension down in X. That's this dimension this direction. You can see that dimension here is 866. So I'm going to make that one station 11 needs to be minus 0.866. So minus 0.866. Now we go to station 12. The automatic tool changer is off. That's going to be the next dimension down in X, which is minus 1.457. And the Y will be this this dimension here, the minus 11.732. It's this station right here that we're doing. Actually, my X is wrong, isn't it? It should be this 2.047. Minus 2.047. Get it right here. So minus 2.047 gets us to this line, which takes us to this station. That's the station we're doing right now. So there's my dimension in Y. There's my dimension in X. And of course, my Z will be the same number, minus 3.697. Now I'm ready to move on to station 13. Station 13, I've got a little bit off the screen here, but that's okay. Station 13 now is setting here. So it's going to be, the X is going to be minus 3.228. Y, okay, the Y dimension is going to be this same dimension, the minus 11.732. And the Z will be that minus 3.697 dimension. Now we're ready to move on to station 14. Station 14, we'll have it listed here. So that's going to be an X of minus 1.457. Y of minus 12.913. And the Z of minus 3.967. So now we have that station identified. So we have one more, station 15, and that station is sitting here, which is X of minus 2.638. The Y is minus 12.913, and the Z is minus 3.697. So you see how we're getting the numbers directly from the print. All right. Oops, I typed in something wrong. There we go. See, I got dyslexic on this one. 3.697. There we go. It's a good idea to go back through them and check through them and look. While I'm looking at it, the axes numbers make sense. Those numbers look like they're right. Last two, turn off automatic tool changer. Again, making sure those things are set right, just looking through them. Make sure automatic tool changer is off. Okay, because what happens if the automatic tool changer is left on, what will happen is even if you have a tool in that station, it will disappear until it's used. It won't show up until it's used. So it's important, especially on a Swiss machine, that any tool that's mounted in the station is going to be used properly. Okay, so it's display. We want it to be displayed, so we want to make certain that this automatic tool changer switch is off. That's very important. Okay, so now we're done with the main gang turret. We're ready now to move on to the next component. Well, now that we've added the stations and axes, there's one more component we need to add to the main gang turret, and that's going to be the solid model itself. So we select on solids, and we're going to say we're going to define a new solid, and I'll give it a name. I'll call it the main gang. Give it a color. You choose that. I'm going to leave it solid. I'm not going to make it transparent. And I'm now going to select our STL file. And so now I'm going to select the main gang turret that we saved a moment ago. Now at this point, one critical decision you need to make, and this will depend upon the way that you manage your files, is whether or not to embed the STL file into this machine setup. Now, the difference here is that if I do not embed the STL file, then I need to have a clear path to read this file every time I open up a program or the machine setup that is using this STL file. Pros and cons here are that if I do not embed the STL file, then the actual Esprit project that I'm working on will be much smaller. I will not have all this the extra STL files embedded in those Esprit files. The disadvantage is that if I were to want to send this file to a colleague or to Esprit for support or anywhere else, if you do not embed this file, if the person you send it to does not have this exact same path and this external STL file, their simulation won't look like yours. So I can't really tell you which way is better. I will tell you this, that if I have a very complicated, now this machine setup is not terribly complex, but if I have a very complex machine setup, and if I'm working in a dedicated shop and it's me and my machines, then I'm probably not going to embed the STL files. But if I think for a minute that I'm going to be sharing my machine setup with colleagues or other people, or I might need to send this file to other people to look at, then I will turn on the embed STL file selection. Because once this is embedded and saved, then this STL file is actually an integral part of this Esprit file. And so it will actually embed that file into the Esprit project. Now you will find that all of the files that I have in this tutorial have this switch turned on. And that's just because if I didn't, then you would be forced to use the same path structure to find these STL files on all of your computers. And instead of having people that buy our tutorials to have these kinds of problems, then I do, for the tutorial at least, I embed my STL files. Now to help make this easier on my resources with regards to simulation, I used a technique we showed earlier by reducing the tolerance to make your STL files much smaller. So we've embedded that STL file, we've added the stations, we've added the main gang, we've added the axes. Let's now hit our OK button. And so now at this point we're done with this particular main gang turret. Now I've got some extra stuff here that we had put on before. I'm going to grab all that extra geometry we had before and just delete it. Don't really need it. Actually I'll grab all and I'll put a box around it. There's a dimension out there too that I'll delete. Now, since I've added that one component, if I now go in, and I'll change my work plane back to XYZ, and you see where the orientation is to XYZ now. If I now go in and decide to turn on, let's say I decide to run a simulation. Now, there's nothing in this file, but just by going into simulation and firing off simulation, any of the components that are in the machine setup will appear. In this case, you'll see that we now have our main gang turret sitting here. It's sitting on the stock, and we have this large chuck located here. Now this chuck, we haven't dealt with that yet. We'll be dealing with that shortly, but you see how we have our main gang turret is actually sitting in this location. Now, one thing I really don't like is where this orientation is here. I obviously want to move it up in X. So one of the things I can adjust quickly is I can go into my machine setup, and on the assembly page, main gang turret, I'll add a home position in the X-axis. Let's say 2.5 inches, for example. If I fire off my simulation, it's now going to be setting up that 2.5 inches. So we now have our first component added to our machine setup. Let's now deal with the next components. Let's go to Setup, and let's now go into the assembly page. And we're ready now to add the next component. Now, what we could do is we could go ahead and deal with this spindle that we had. If you recall, we fire off simulation again, we got this spindle sitting out this way, and we also have the stock is pointing off in this direction. And if we relate that to our drawing here, we see, of course, that really the stock, as we start a program, should be sitting over in this direction, and the stock's going to be fed going towards the sub spindle, which is located here. And that's because this particular machine setup, with regards to the spindle, is set up like a traditional turret lathe would be, with the chuck on the left, the stock starts on the left, and the tools come in from the right. This Swiss machine, which is not unusual for a lot of Swiss machines, is exactly the opposite. The main spindle's on the right, the material is fed towards the left where the sub spindle is located at. So let's take care of this spindle while we're at it. So we'll stop that simulation, we'll go back into Common Machining and Machine Setup. We'll go into the assembly page, Main Spindle. Main spindle name, that's okay. I'll get rid of the -1. Don't really need that. It is a main spindle. One thing I will change immediately is this orientation setting. And the orientation setting is going to point the turret. In this case, I'm going to use, based on my sketch, I have Z plus pointing to the left and Z minus pointing to the right. So that's what I'm going to use here. I'm going to use this one here, right plus, which means going to the left here is a plus direction in Z. Now the next thing we need to look at is a home position in Z. Now, instead of thinking about the picture you saw a moment ago when we ran simulation, what you really want to think about here is really what the real main spindle in this Swiss machine is. And that is that it's actually a spindle. The main spindle is actually not this, but it's actually a main chucking is back behind the part that's holding the material, and it's feeding the part in and out. All that's happening up here is this is a guide bushing that's going to guide the part, and as it's being fed in and out and held at a position behind the part. Now that position where that is behind the part is where I'm going to reference my home position in X, Y, and Z. Now typically what you'll want to do is you'll want to identify a position that represents where where that chuck's going to be located when you start a program. And typically what that's going to be, let me turn on the chuck component so you can get a better feel for this. Typically what that's going to be is a position back behind the part, and this is going to, the distance from this location to the bushing is going to be the amount of stroke that you have. When we refer to stroke, what we mean is the amount of travel that the material has in one direction, going out, material being fed out of the spindle. The amount of distance we move out of the spindle before the chuck, it has to be rechucked. For this chuck that's holding the part has to be picked up, moved back, and grab some more material. So I'm going to designate a position of being about 8 inches. I'm telling it that we have about 6.5 inches of stroke before we run into the chuck. I've identified my bushing here to be about 1.5 inches long. That's what I have here. So we're going to go in and we're going to identify on the main spindle. I'll again change this back to, take that off, change this back to plus. And I'm going to change this home position to a positive 8 inches. Positive 8 inches. Now that positive 8 inches is not relative to the axes that we've identified here. It's relative to what a spree sees that z-axis to be. And a spree sees, like normal Cartesian coordinates, it sees this direction is positive. So 8 inches positive is going to be setting out here. Next thing we need to look at is geometry, and we need to identify the physical geometry of that spindle. And so we'll identify that as being, let's say, about an inch 350. I'll put the chuck length of, say, 540, 550. I'll make the jaw lengths fairly small, and the open distance, same thing, so we can visually see it. 1875 there as well. Okay, hit my OK button on that. Now, the only other thing I will go ahead and change while I'm here is I'm going to go ahead and address the issue of my bar stock size. I mentioned how we weren't going to deal with this stock yet, but for the exercises we're going to be using, we're going to use a bar diameter of 7/8, and my maximum diameter, or the maximum diameter I can actually work with, is going to be 1 inch 496. That's the biggest diameter I can turn. That's the biggest that'll fit through my guide bushing. Total bar length, I'll tell it's about 24 inches long, and the part we're going to machine for our first part is 7.14 long. Next thing I'll plug in is a starting position for my stock. I'm going to tell it has 10 thousandths worth of stock sticking out of the part, and so we're going to be working with 10 thousandths worth of stock to be faced off. So I'm going to identify and set this to a minus 10 thousandths. Now again, that number, that minus number, is relative to the really to the world coordinate system in turning. So minus 10 thousandths is the correct value. Now let's hit our OK button, and I can close these components for right now, and let's fire off a simulation again. Now what we'll see a little different here, let's roll it around to the right orientation, is now what we see this chucking device 8 inches back on the part. Our stock is pointing in this direction, and it's sitting just like this. Okay, and that's good. And if I get a top view, that's how it's going to sit in a turning orientation. Z0, and then Z is going to be feeding it to the left. All right. Excellent. All right. Now let's add some other components. Let's go in to on the assembly page. Let's go ahead and add this on the main spindle. Let's go ahead and finish it since we were in the process of modifying that. Let's talk about the axes. There is going to be an axis. This main spindle does in fact move. When it's gripped out here, that part's going to move in and out. Now the axis we're going to use is from our drawing. It's this Z1 axis. Z1. So we're going to identify a Z1 axis. We're going to go in and say axes, Z, new axis. I'll call it Z1. It is linear. It does move along the Z-axis vector, which this is correct. And now I'll plug in a minimum and a maximum distance. I'll say it can move minus, say, 1.5 inches, and it can move plus, let's say, 24 inches. And again, if you know the right numbers, plug them in. That gives us an axis for the main spindle. So now the Z-axis is going to be driven by the main spindle, moving the material in and out of the part. Last component we'll add for the main spindle is going to be the solids themselves. So under the main spindle. Now in the main spindle, if we look at solids, there really aren't any solids for the main spindle, and they don't need to be. You could draw something up. We could have created something for that main spindle, but we're not going to. Now you may think that the solids here really should have been these items here, these items, but that's not true. Because if I had attached these items to the machine setup, if I went into assembly, main spindle, solids, and I had added new solid and added these STL files, then what would happen is when the material is being fed with the real spindle, which is back here holding the part, gripping the part, then what would happen is this would all move with that. So in other words, these would move as the material is moved. And I don't want that to happen. I need this to be stationary. This is going to stay stationary. So these are not going to be added to the solids under the spindle. They'll be added elsewhere. And we'll talk about that a little bit later. But just keep in mind, like I say, in this case, we're not going to have any solids attached to the main spindle. What we see on the screen currently when we run fire off simulation, that spindle right there is a stock spindle that's being used to grip the part. That's the only thing we want moving. We want that to move, but we do not want the real spindle that's sitting here to actually move. We want it to stay stationary. All right, so we're ready now to go to our next component. And the next component we want to add, I'll turn these three off, is let's add the sub spindle. And let's get around where we can look onto the sub spindle. And we can see the settings for the sub spindle. And now we're ready to go ahead and define the sub. To make this a little easier to see, I'm going to turn on my shaded wire so I can see those other tool stations. And we'll go back into machine setup. Now what we're going to do is we're going to add a new turret. Now yes, this is a spindle, but the function of this piece of tooling or this item is not just to be a spindle. It also is a turret. There are stations on this to be used. So the fact that there are stations on this really takes precedence over the fact that there is a sub spindle. So what we're going to actually do here is I'm going to identify this as a new turret. And I'm going to give it a name. Let's call it the sub turret. And I'll call it turret number 2. And I'll go into its diametral, is fine. Now again, it's going to be another custom. Now if it was a gang, I could use a gang turret. I could identify these dimensions as to where those stations would be on a gang block. I would give it the dimensions of the block, and then the tool separation would be the distance between these stations. But that's not what we have. We have a custom in this case. Now, the only other thing we want to look at here is, let's pull up our picture, is we do have a home position. And in Z, I want that home position to be back here somewhere and back away from the part this way, which in machine terms, or actually in Esprit terms, that's going to be in the Z minus direction. So I'm going to plug in a value there. I'm going to plug in a distance. I'll make an arbitrary value of, say, minus 8 point, let's go make 8.82. Okay. I'll turn on my ensure tool number matches. I'll set my move to tool change to be Z first. Good. And that's all I'm going to change on this page. Start stations. Well, we'll talk about stations in a minute. Let's go down now. Let's go ahead and add the axes that takes place here. And if we think about the axes, now first of all, there is not an index. And when you add a new turret, you'll automatically get an index because it assumes it's going to be an index turret. So it adds this axis as a tool change axis to index the turret. Now we're not doing that, so we delete that index turret, just like that. So anytime you add another turret, you're going to need to make sure you do that. All right, if we take a look here, we're going to have, it shows it to be a Z, a Z2, second Z. And then it has what they call an X2. Now notice this X2 is going in the same direction as Y. And of course really, X is moving up and down this way. So it's labeled as X2, and in the code it's going to be coded as X2. But from a the kinematics portion of this, it's actually going to be moving along the Y axis. So I'm going to define the Z as the primary axis, because that's the primary motion of this turret. So I'm going to identify Z first, and I'll say a new axis. And I'll call this one Z2. And under Z2, it is linear, and we do have our settings of 1 inch in my vector for Z, which identifies the direction. And the minimum maximum, I'll tell it the minimum is 0, and I'll say the maximum it moves a positive 15 inches. Okay. And again, that number's subjective. I might make that number match up with this number, 8.82. I can say, well, let's say it moves the same 8.82. I'll just use that method. How's that? Okay, now we need to add the next axis. So I'm going to go to the next axis. Now, from the label standpoint, this next axis is X. But really, the motion of this is Y. It's going to move this way. So I'm going to actually tell it it's a Y axis and say new axis. But what I'm going to do is make the name of it X2. A little confusing there, but that label, you see the contradiction here. I mean, this can't be X and this can't be X. And so from a Esprit's perspective, this is the X axis. This label is a labeling an axis that moves along Y. So it is a Y axis in the sense that it has an axis vector in Y, but it's labeled as X2. Now let's take a look. We'll plug in some numbers here. we'll say that it has a 0 in the minus position. Let's say it can go a positive 15 inches. So now we have our axes defined, and now we're ready to talk about our tool stations. Now, on our tool stations, there's really going to be 4 stations here. You may look at this and think, well, there's just 3, but really there's 4. We still need a spindle here, and so what we're going to use is we are going to define a sub spindle, but that sub spindle is going to be mounted on this turret. So the first station on this turret is going to be for the sub spindle. So we're going to take away a couple of these stations. I'm going to grab 5, delete, and delete one more time, and we have now 4 stations. Now if we look at our picture, we see that these are labeled 20, which is the sub spindle, 21, 22, 23. So I'm going to actually name my stations those same numbers. 20, 21, 22, and 23. There's no reason for this not to match up, these numbers to match up with what you have in your machine, so it makes it much easier when you depict tools, you know to look in station 20, 22, etc. Now let's talk about the settings for those stations. I'm going to tell it it's a holder base, default, no automatic tool changer, and set this guy to 0. Right. Take a look at 21 now. Now for 21, we're going to, again, holder base again, 0. But now what we're going to do is we're going to plug in the dimension to move it off center. Now, picture, if you will, this direction is the same direction as our stations on the main gang turret. So this is going to be a minus in Y. It's going to minus direction in Y. So we're going to tell it this station is at minus 2.75. Now there's one other thing. Let's hit OK. Get back in this part so you can see it a little bit better, zooming out. You see these stations aren't flush with each other. So if I get a different view here, you'll see that there's actually 3 inches from the face of the sub spindle back to this back edge here. It's back 3 inches to there. So what we might want is it's 3 inches back to it, so where we're going to locate the holder. And I've identified a spot in the holder kind of like inside of the machine, a distance away from the end. So the holder will actually start here and come out this way. You could define it exactly to be what this edge is here. So you can make that distinction, which that distinction is actually 2.5 inches to here. 2.5 inches to this location. I'm going to use the 3 inches for my purpose. Again, you can adjust all these things as needed. So we go back in, and we now can go back into the assembly page. Sub turret station number 2 now is now going to be a Z of, in this case, minus 3 inches. So it's moving in minus direction in Z, 3 inches. And 22 is going to be 0. And it's going to be this dimension 4 1/4, so minus 4 1/4, and minus 3 inches again. And now we have 24, which is 0, and minus, I skipped, no, that should be 23, shouldn't it? Silly me. 23, there we go. 0, that should be minus 5.75, and minus 3. Now we've set the home position. We've set these values in where we want. Let's hit oh, one more thing before we move on. Let's add that solid for this. So under solids, we're going to add a solid to this. We're going to say, give me a new solid. We'll call it, this will be the sub turret. And we'll give it a color. We want a different color if we wish. Kind of our call. You pick colors as you prefer. And the location will be the default. I'm not going to identify an axis or anything because it doesn't move with one axis. It moves with both. So by saying default, we're going to use both axes. We browse and we find the sub spindle turret, and I am going to embed that here. We talked about that earlier. Now let's hit our OK button. And now if I come out and kind of zoom this thing around a little bit here and change my work plane back to XYZ so I can see my point of reference a little bit better. Roll it around like so, and if I fire off my simulation, we now should see the sub spindle with its graphic associated with it, the main gang, and this. Now, so you can see now that minus, it's again minus direction relative to a spree, minus 8 inches to here, and then it was another minus 3 inches farther from the face to these locations here. All right, so you can see how we've identified that, and now we have the sub spindle. Looks good. All right, so now let's go to the next component. We'll turn that off. We'll turn on this T31 through 34, and we'll get a top view on that. Take a quick look at those. I'll zoom it down a little bit and drag it out of the way. So we can see that we're 1'260" between stations. So clearly we could define another turret. It could be simply a gang block turret if we wish, but we do have this graphic to use, so we will use that. So we'll now go in and we're ready to define the next. So we go in and tell it we want another turret. So we do a new turret. This turret now is going to be, well, let's say it's the end gang turret. Now I'll call this turret number 3. And it's not an index turret. It's going to be a custom again because we have our own graphic. But again, keep in mind, if you did not have this graphic, you could have gone into gang geometry. I could have said the turret size in X is this length, which was, let's just say it was 3 inches. I'll just say that. The turret length in Y would have been 354, excuse me, this dimension here. And the turret size in Z, which is the thickness, would be whatever, let's say 2 inches. And then this separation distance would have been 1.26. So that, combined with telling it has 4 stations, would create a block that's this dimensionally in size and has this distance between stations. All right? In fact, let's hit OK. And let's just, for grins, go in and let's tell it has 4 stations. So let's get rid of this station and this station. Let's just hit OK. And I just want to see, close, 3" 430. If I fire off simulation, you now will see that other block. Now, I didn't tell it where to go home, but that block is actually sitting there. And where it's sitting at is right there. So you can see where it's placed a block right here. And that block was defined by the information plugged in. Now, there's no stations in it because there's no tools attached to it. All it does is show the block, and then the tools would stick out once you place the tools on that station, in those stations. Okay, but that shows you a little bit about how you can just very easily and simply go in and plug in a very simple scenario of defining your own geometry to create a block like that. And of course, we would give it a home position. In this case, as a matter of fact, let's give it a home position. Let's say Y is going to go plus. Let's move it out, say plus about 9 inches. And let's pull Z out away from the chuck to be minus, let's say about 2 1/4. I'll turn this switch on. Let's hit OK. Again, these numbers are somewhat subjective. You'd want to make sure your numbers are correct. But anyway, here you see that block. Now that block is sitting here. Now that's not a big stretch from this picture. You see how this block is actually sitting like so, and it would be in our picture like this. So you see I'm just positioning that block out like so. All right, so let's go back to our top view here, and let's now go back and define a few other things with this. Zoom it down, drag it over, and open up our machine setup one more time. And assembly, end gang turret, got our axes. Now on axes, let's take care of the axes situation here also. For axes, we don't need the index turret obviously, so we delete it, but we do need to add an axis. And that axis is going to move, as we see, look in the picture, along X. It's this X3. So we're going to define an X-axis, a new axis. It's called X3. And in there we will plug in the amount it's going to travel. Let's say -2 + 2. It's got 2 inches of X travel. And again, this would be able to take, if I had a milling tool, I could use it to mill a part held in the sub spindle. Okay, rest of that looks good. All right, so now let's talk about our stations. Now, numbering the station-wise, the stations really should be numbered like they are on the machine. So this one would actually be 31, 32, again, like the picture shows, 31, 32, 33, and 34. So we got 31, 32, 33, and 34. Now let's make the edits to these. We're going to treat this kind of like the sub spindle in that we're going to use the holder base. The tool change position, we'll set that to 0 and 0. Okay, and I'm going to go ahead and shift this position of this out. I'm going to make the holder not start right here, but actually make the holder start in the body of this. I'll do that by shifting it 1 inch in Z. And we'll talk about that more when we get into putting some tools in these stations. Because once we're done with this machine setup, we're going to put some tools in the stations so that it will look correct. We'll make sure that we have our tools defined properly. All right, let's move on to station number 32. Station 32 will be a 0 here. This number will be the 1.26. Now, the value I'm plugging in is going to be a positive 1.26 because that's going the positive direction along that axis. It's opposite of the gang turret and the sub spindle, which is going this direction. You kind of can picture it. It's kind of like we're sitting on the sub spindle looking at this turret. And the Z, actually I'm going to change that back to 0. I shouldn't have done that. We'll leave that at 0. We'll adjust that if we need to later. All right, now 33. Go to the next one. That's going to be a 0 here. And now this number will be twice this value. So that number will be 2.52. Then we go to station 34. Change this to 0. And now this is going to be the third live tool, which would be this times 3. 3, 6, 780. So 3.780. Okay, so we do that, and then the last thing we would do is go to solids, and we'll add our solid. Do solid. This will be the end gang. And go in and grab a color. And in terms of default axis, that's fine. And I'll browse. This will be the end working turret. And embed it. By the way, also you can do is you can also make any of these components, these solids, transparent if you want to be able to see through them. I really don't want to do that on this Swiss machine. I want to be able to see everything, but you can on some machines, especially if you add other components to this. So we hit OK. Okay, now let's go ahead and we'll turn that layer off. Now change back to XYZ, and we'll go get an isometric view of this thing a little bit. Like so, and let's fire off a simulation again. Okay, so now we have, oh, see, look here, we got that other block in there as well. So let's stop simulation. Let's get rid of that other block. Assembly, end gang. Now, why do we have the other block in there? Well, that's because I left this on gang. And what gang did was it used the geometry we typed in here, but then it also added the graphic from here. So what I really needed to do is take this and change this back to custom. And when I do, it will not use the graphic or the information typed in under geometry. So let's fire that off again. All right, there we go. And there's our other block. So now we have this block, which is offset, setting here, and that's what that minus 2.25 inches did, was it offset this out this direction. So now it's sitting there. There's this, and here we have this information. The only thing we don't have here is we don't have our spindle solids that we created earlier. We don't have those listed there. Also, there's one other solid that I had in the part I didn't talk about. That's called the base. And the base is just a kind of a backdrop. So when you have the base there, you can have these other items, and it looks like a wall, if you will, on the machine. It makes it a little bit easier to visually see. So let's I forgot to do that. Let's take this and save this as an STL real quick. So I grab that. I do a file, save as. Go down and select an STL. And I'll call this the machine base and save it. Okay. All right, so now let's go back into the machine setup. And if we go into assembly, now if you look at these components, matter of fact, these are all the components we need to add next. Really, none of these components need to move. They all need to stay stationary. And if I attach them to any of these 3 turrets that we defined, well, it's going to be trying to move these with those turrets. So what we do is we add those components to the machine base. The machine base will stay stationary. And I go to solids, and now I can add solids underneath that. So I can add a solid. Let's say I'll add the base. Give it a name. I'll give it a color. I'll make it, I'll use something like that blue color that's there. But I will make it somewhat transparent. I want to be able to see through that. And I'll go in and browse for the machine base there and embed it. Now I'll add a second solid. I'll say new solid again. And this time I'll add the spindle base. Now this name is not the name of the file. It's just a name just so you can remember what you've plugged in. So we grab the next one and see what color did I have. I had kind of a, oh, let's see. I had this kind of a brownish color here, right there. That'll be good. Now, I'll make it solid, so I don't really need to. Actually, I might want to see through that one a little bit too. I want to be able to see the stock inside of it. So that'll be the main spindle base right there. Embed it. Do another solid. This will be the spindle nose, and that color was, let's see, what is that one? That's this color, I think. And I'll make it transparent, about halfway transparent. If I go all the way, it'll disappear. So I can see halfway through it. Main spindle nose, embedded. Embed the last one, yes it did. And let's add one more solid. New solid. This will be the guide bushing. And I'll make it a bright color like this orange. And I'll make it transparent as well. Maybe not as much transparent, but transparent. And I'll grab guide bushing and embed. Now we'll hit our OK button. Now we turn those other layers off. There we go. And let's now go in and fire off a simulation. Get an isometric view so you can see. And now we've added those other components. You can see how we can see through this back wall, and that way it'll help us to see this chuck, so we know its location of the part. We can see all of the components. We can see through it like so. And now you'll notice we have this orange guide bushing inside. And we'll talk more about the guide bushing a little later, but just so you know, the guide bushing I've defined is not the size of the part. Okay? And the reason it's not is I need to have this part be able to move in and out without anything touching it. And I need to do that so that I can use simulation properly by having it set to either tool and collision detection, either tool and holder, or set it to full. If I use that, and what it will do is it will detect this hitting into a solid chunk here. So really, I just have this bushing is really not anywhere close to the right size, and it's by purpose. That way I can make sure I can see the material moving in and out, but I have a nice gauge for where this bushing lays, which is actually along this spindle nose area. And so this is the length of my guide bushing, is this length here in this machine. And if you've dealt with any Swiss machines, you know the concept of guide bushing. We'll talk about that a little later when we get into actually doing a part. But at this point, we've actually created this machine setup. And it looks correct. Everything is at home position. This turret's at home. That turret's sitting over here out of the way. It looks like what we want to work with. So this is going to be our baseline for our projects we're going to do in our Swiss tutorial. We'll be using this machine setup with turning tools located here, milling tools, drills, etc. And we'll be going through a couple of different Swiss oriented type projects. Now, once I have a machine setup defined to this point, one of the things I might do is I might go into setup, and I might do a right click in here and save this machine setup. And you notice that when I do, I already have one called Swiss Masterclass. And that was already loaded with your files when you installed the software, when you installed the files from the tutorial. And that is this particular machine setup. So I've already saved it, but you obviously could save it, put a different name, and you could save that yourself as well. Now, when you save that, of course, it won't be saving all of these solids in here. These solids won't be saved as part of that, and that's fine. There's no reason for them to be there. Once they're embedded in the machine setup or directed to those with regards to their path, you don't necessarily need to save that as part of the file. Now, if I were to want to save a template file at this point, if I did a file save as and say, okay, give me a template file, which, by the way, we do have a template file already saved here in this tutorial, the list of files in the tutorial already. This template file would, in fact, include all of the items on this layer. So it would include all the solids from the part. So I personally probably wouldn't make a template file that had all this extra, baggage, if you will, inside the file. This file was a unique file because we had all of these solids in here designed primarily just to kind of, again, give you a feel for how to define a machine setup. And if you decided to draw a few things, it could be crudely constructed like these are, or they could be something quite fancy, or you might get that from your machine tool vendor. What we do is we're just simply showing you how you can take and convert these solids into something usable inside of your machine setup. So at this point, I think I'm done. Oh, one more thing on this machine setup. stop this. Let me turn this off for a second. Actually, one more component we forgot to add. I'm really nowhere near done with machine setup, by the way. I'm done with defining the solids. Kind of got excited there, thinking I was done with that part, but I'm not. One other thing, we have a main spindle identified, and even though we defined a sub turret, that's not the same as having a sub spindle. In fact, if we look at this part, you see that the sub spindle over here consists of a hole. It's just a hole in the part. So it's really not a sub spindle. It's just a mount, if you will, for the sub spindle. So one of the things we have not done is we have not added a sub spindle to this. And that's what we're going to do next. So we go to Assembly, and now we're going to add a new spindle. Now in this new spindle, it just says spindle. I'll give it the name. It's called a sub spindle. And it's spindle number 2. And then what type of spindle is it? Now, normally you might say it's a sub spindle, but really in this case it's not. It's a turret spindle. That's because this spindle is actually part of a turret. It moves along with this turret. And now below that we tell it which turret it's on. It's on the sub turret. And which station is it located in? It's in station number 20. And now we look at our orientation. Now we're setting in this orientation here, okay, for this. And that matches up. Actually, it should be this orientation, Z minus. That matches up with the picture showing the Z goes in the minus direction going this way. So that sets up left minus. Now, home position. I'm going to make sure I plug in a home position that matches the home position of the sub spindle, that minus 8.882. That was the dimension we had up in the, as far as the sub turret, you see up here, this dimension, we want the sub spindle to be at the same home position. Now, as far as geometry goes, we'll define a similar spindle as what we used on the main. So I'll make it fairly small, inch 450. I'll make it, say 540 there, 0. I'll make the jaw length 0. I'm not going to try to show any jaws here in this. You could if you want to get fancy, but I don't think it's necessary for us for the tutorial at least. And we'll hit OK. Now, there are no solids associated with this sub spindle, but there is an axis. There is an axis. And so we want to define that axis and use that axis. That axis is actually, if you think about it, that axis, there is an axis, but that axis is going to come from the sub turret, this Z-axis here. So you see how we don't necessarily need to add a separate axis. If I had another axis here, this would be telling us that the sub spindle can move independent of the sub turret that it's attached to. So I'm not going to add another axis. The Z2 has been defined up here. So it's not necessary for us to add the axis down here. Okay, so now if I hit OK and I fire off a simulation, we should now see a simulated chuck located inside of the sub spindle. And that's the actual sub spindle that's located in the sub turret. So there's two components here, a sub turret and a sub spindle. By the way, we'll see that some of the round components here are faceted. That's because of the tolerance that I chose when I created the Stl files. If I wanted that to look smoother, then I obviously could have decreased the tolerance and to make that a much smoother drawing. I don't really care about that, but that's something you can do to increase the graphic visualization of those components. Okay, good. Stop that there. So now at this point we are at a very important junction, and that is that we've really completed all of the items on the assembly page. Now there is a tailstock listed here, and you can't, by the way, delete a tailstock. There's no delete here. But I can simply tell it that the tailstock type is none, which means there is no tailstock. And so that's what we have here, is no tailstock listed. So let's hit OK. And now we are finished with that portion of this tutorial. Well, now that we've finished the graphic portion of our machine setup, we now need to move on to a bit more of the details, and that is we need to go into machine setup again, and we need to now go to the NC output page. And this is critical because this is what's going to determine how the NC code is going to be processed for our particular machine. Now, the first thing we need to make a decision on is the NC output order. How do we want to output our NC code? And there are three choices. We can output it by spindle, by turret, and by head. Now, typically in Swiss machines, virtually all Swiss machines are going to use the head method. Just so you know the difference between spindle and turret. Spindle and turret gets used primarily on machines that have twin turret and twin spindle capability, where the NC code is output as a separate program for each spindle or a separate program for each turret. Now, in the case of a Swiss machine, that's not terribly practical, because typically what happens on a Swiss machine is that groups of turrets or gang turrets or cross slides are gathered together in what's called a head. A head is, if for lack of a better term, is a collection of turrets and sub-elements that belong to that head. Now, the number of heads is important. This determines the number of programs that need to be output to drive this machine. Now, most common is you will have a Swiss machine that has two heads. And that's what we're going to use in this case. But understand there may be more. There are machines out there that require three heads, or in that instance, three programs to be sent to the machine tool. We're going to be using two different heads. Now, what's important is that when you make a selection of head and you select that you're going to the number of heads you're going to do, you'll now have under head ID, you'll have either 1 or 2. Now, what happens is when you pick 1, everything else down at the bottom, all of this information across the bottom, is all relative to head 1 of that machine. And when I pick on head 2, all the items below are relative to head 2. I'm going to hit on head 1, and we're going to talk about the settings we have here. First, we have a setting called sync string codes. And let's talk about what sync string codes means. Sync string codes are a special type of synchronization codes. Now, they do work in conjunction with the sync codes that are listed over here. Probably easier to start with sync codes. Sync codes are going to typically be your either M or P values. Typically in Swiss machines, these are M codes. And they can work in any increment. Let's say I want to work them in increments of 1. And I can start these at any number. Let's say I wanted to start at 500 and go to a total of maybe 599. That'll give me 99 sync codes that I can use. Now, on a Swiss machine, a lot of times just a sync code by itself is not enough. There are certain functions that take place on a Swiss machine, and primarily dealing with either part transfers, cutoffs, things of that nature, that require unique types of codes. And for that, we will use what are called sync string codes. And we simply will dial in how many sync string codes we want to use. Let's say, for example, I wanted just one sync string. And I go in and I dial this back up to sync string number 1. I say, how many number of syncs do I want? Let's say I want one sync string. Then underneath the ID, it'll have one sync string, and it will have a value you enter in next to this. This value is used to be output to drive this special type of function. In this case, I'm using an M220, which is a unique function that has to do with synchronizing relative to a cutoff on a very common Fanuc type Swiss machine. Now, basically what you do is you'll identify how many of these sync strings you wish to use. Now, you don't necessarily have to use any of them in a program. You simply can cover your bases and look at any special sync string that is going to be output. Now, in this field is what the actual output will be. Now, it may be an M220. It could be a G value, G230, for example. It could be even some machines require an unusual set of characters. Some other unusual set of characters that might be output. And your job is to simply enter in the values that make sense. And then it's basically you're creating this list of special sync codes for your machine. In fact, I will use M220. And what we do is we'll identify how many of these sync strings we want. Let's say I wanted 6 sync strings. And so what we do is we look under the second sync string, and I would plug in after the first sync string. Let's say the second sync string I wanted an output of M221. And let's say the third sync string I wanted an M222. And I'll go to sync string number 4. And I'll do an M, let's say 230. 230. Go there. And I'll go to here and I'll do a M232. and I'll do the sixth one to be an M2, actually 232 there. I'll do M231 on number 5. So now we have all these different sync codes that have different values next to them. Now we'll talk more about how to use those sync codes when we actually do our next exercise, which is going to be an actual part, and where we will use some of these sync strings in conjunction with our programming. So now what we've done is we've identified those sync string codes here and here. Now, as I mentioned, when I change this to head 2, you see how this area right here stays the same, and it should. It stays the same. However, the next area from here down where it says head 1 program output, everything from here down is going to be relative to head 1. When I change it to head 2, everything from here down is relative to head 2. Now let's deal with head 1. Program name. This is just a label, if you will, be output in your code. Let's say Swiss tutorial. Program number. This will be on any of the FANUC or FANUC type machines. This is the program number you wish to use. Coordinate mode, absolute incremental. And notice, by the way, when I switch back to head 2, this all becomes blank. Because again, these are separate, unique settings for head 1 and head 2. Again, keeping in mind that we're basically constructing this so that we output 2 programs to drive this machine. One labeled head 1, one labeled head 2. Now below that we have a very important section. This identifies the relationship between the turrets, okay, what we've called turrets, and the head. In other words, head 1, what it wants to know is what's the relationship of each of the 3 turrets that we've identified and this head. And you have 3 choices. It can either be never, meaning that this head never belongs to, this turret never belongs to this head, or this turret could be exclusive to this head, or this turret could be shared with this head. In our particular case, head 1 is always going to be responsible for dealing with the main gang turret. The main gang turret is never posted on head 2. So we could set main gang turret to exclusive, which means it always works with that turret. Now we could look at sub turret number 2, and that is the turret on with the sub spindle. Well, that would be possibly shared. There could be operations that we might use, that we might cut with, that we might want to be part of head 1 or head 2. Now I'm going to go ahead and hit OK here. I'm going to go in and turn on our machine again to get our bearings. As I mentioned, I've told it that this particular turret is only used with head 1. Head 1 being controlling the main gang turret. Head 2 is going to be for the sub spindle and those stations. Now, those stations here may well be output code-wise with head 1, depending upon the machine. It may be that we output those with head 1. So in this case, I might elect to have this portion of the sub spindle control, these 3 stations, if you will, controlled on head 1. And then but I might want the sub spindle activity to all be controlled on head 2. Again, this is going to depend upon your machine. So I'm going to go in and my NC output page on head 1, which is what I'm working on right now, head 1, I'm going to identify that I want the sub spindle, the sub turret, to be shared. But then if we think about it, the end gang turret, do it one more time here so you can see. The end gang turret, well, I would never really use the end gang turret except with the sub spindle, would I? These tools sticking out can't do any good over here on this side of the part. They'll only work when the material is being gripped by the sub spindle. So we're going to have this particular end turret only work with head 2. So it'll be part of head 2. So head 2 will consist of the sub spindle and this turret, whereas head 1 consists of the main gang and these 3 stations here. So that helps us to make our decisions as to how we're going to set this up. The end gang turret would never be used on head 1. So I would identify that as being never. Now the next thing we would have is, do we want any of the relationship between the heads and the spindles? Do we want any of these spindles to be exclusive or shared or not used on head 1? Now head 1 obviously is going to be working on the main spindle. No question about that. But would we ever use the tools in head 1 on the sub spindle? And really, if you think about it, you would not, because the tools really can't reach on the sub spindle. With the exception of the end turret stations, these stations here, let's close this again. If I have tools sticking out of this direction on here on the main gang, those tools could be output on the sub spindle. in which case I may well output those stations as being part of head 2 here. So in this case, in essence, this particular end turret, this particular main gang turret, could actually be used both on the main spindle and with these 5 stations here used on the back on the sub spindle. So what that tells me is that the best choice here is going to be a shared environment. So both, in other words, head 1 can use both spindles. Now we move to head number 2, in which case it blanks this out, and I can again say the same, just tutorial, and I'll make the program number slightly different, which would be typical, because it would have a different program number. And then now we look at the relationship on the sub spindle side. So basically what we want to know is, could the sub spindle, should the main gang turret be used on the sub spindle? And the answer is yes. Those 5 back stations we talked about could be. What about the sub turret stations? Could they possibly be used on the sub spindle? Well, technically no, other than the one station that is the sub spindle. So I'm going to leave that on shared. And then the end gang turret, I'm going to change this to exclusive, because that end gang turret can only be used on the sub spindle, and it can only be used on head 2. So you can see how we've basically identified that both of these turrets can be output both as head 1 and head 2, whereas the end gang turret can only be output as head 3. Now we go back over to the spindle relationships, and in this case, of course, the activity of the sub spindle can be feeding material against a tool on the main spindle, and the sub spindle obviously can be used on head 2 on the end gang turret. So I like these settings here as well. So now we've set up this machine setup with all of the kinematics here. We've set up, of course, our basic stock information. We've also set up all the NC output information here. And of course, now would be the perfect time to do a right click and save. And we would save off this machine setup and use it over and over again. In which case I'll pick here, I'll hit save, and now I've just saved that machine setup. Alright, so now we can use that machine setup with future projects for this machine, and it has our sync strings, our sync code settings, it has all of our relationships between each of the 2 heads that have been identified, and so now it's ready to go. So that takes care of the machine setup portion of this tutorial. We're ready now to move on to the next segment, which is going to be using this for an actual operation. Most notably, tools. So you have no tools in any of the stations. So it's important for you to know how to place these tools in the stations. So that's what we're going to talk about now, is defining those tools. And we're going to start by dealing with the turning stations here on the main gang turret. Now to do that, we first need to get our bearings and understand that the distances between here, you see that the width between in the slot is 443, and the distance is 886 from here to the next slot. So 443 is the key number that we're looking for. So let's go define a tool. Let's put a tool in, let's say, station number 1. We'll put a tool, I'll drag it over so you can see. There we go. We're going to put a tool up here in station number 1. So let's go to Tools, and you will notice that under Tools, matter of fact, I'll close this so we can see a little bit easier. You'll see that we now have all of our 15 stations on the main gang turret. We have all 4 stations on the sub turret and the 4 stations on the end gang turret. Now you will notice as you scroll on down, if you were to open up unassigned, you will see a whole bunch of tools down here, and that's because in this file I have defined a tool for every station. Well, virtually. I think I left 1 or 2 stations out, but for most all the stations I have a tools down here. But and we can obviously move these tools into the appropriate stations as needed, but I want to go through and define some of these tools on our own so you understand some of the unique techniques you must use on a Swiss machine for managing the tool locations in your custom turrets. So let's go define a tool. Let's deal with the turning tool first. I'll do a turning insert. And on this turning insert, I'll make this, let's say, the shape is a trigon. And let's say that it's got a nose radius of, let's say it's a 331. So I'll type in equals 1-/64, tab key, and let's say 0.375 and tab key. And of course that will adjust the edge length and to make that number correct. Now move on to the holder page. On the holder page, it is a turning tool like this. The style holder I'll use is an L-5 lead. Now, shank size, there is not going to be a shank size up here that's going to say 443. So I'm going to pick a 1/2 by 1/2. Right? And I'll leave the rest of the settings as they are, but what I'm going to do now is I'm going to go into here, I'm going to adjust these numbers inside of here. And the key numbers I want to adjust is this A dimension and this F dimension. And so on the A dimension, I'm going to plug in that's 0.443. On the F dimension, it too is 0.443. Now I'll leave the 4-inch length, it's fine. B dimension, I could adjust it. Usually I'll make it the same as A, but again, it doesn't matter here. The E dimension I could adjust, but this will make this a square block tool, tool station, I should say. General, we'll just tell this is a face and turn. And it's going to go into the main gang turret in station 1. And then now we need to make a decision on orientation. Clearly, if this tool is going to be used on the main spindle, and it's going to be used to do both facing and turning work, it should be setting like this, a 4V orientation. So I'm going to set that tool in just like that. So 4V. All right, it says home, home, home. Everything's good, and we hit OK. And now we have a face and turn tool. Fire off simulation. We now show that tool setting up in that station. Now, one thing you will notice is how that tool is actually sticking up too far this direction. And that's just because we identified the end of the tool post, which is actually where the insert is, as the gauge location for this tool. That was a decision we made inside of machine setup when we went into our in our stations, and we identified we were working off the tool point, which is the tip of the tool. I recommend using that. And I could use tool base. We'll take a look what that does. You see the difference here. Tool base does. Tool base is going to simply use the base length as the length for which to locate the holder. I'm not real crazy about that method. I'm going to change this back now and change that back to station 1. Change that back to tool point and OK. Now on that tool, I want to go back in and edit that tool again. Back to the holder page, 443, 443. In fact, I'll make sure this is 443 also, just to make sure. Now what I'll do here is I will adjust, in this case, I can adjust the x-axis of this tool to determine how much of that tool is going to be out of the holder. That's a decision I can make on the tool itself. For example, if I want to move it out 1 inch, I can plug in -1 inch right here in this tool shift of X. And what that will do for me is it will position the tool like so. And see how the tool is positioned with 1 inch coming out this way. I like this method of managing the lengths of the tools coming out of the turning tools, so I can manage that each tool independently can have different lengths to them. So now we have that insert setting like this, and it's in the right position. It would work well for a face and turn. Now, what if we wanted to do, let's say this part required some back turning. Once we get the material fed out, we need to come in and do a back turn. So we need the insert pointing in the opposite direction. So I'm going to define another turning tool. I'll do that by going in to define another turning tool. And we'll use the same insert size. And on the holder, I'll use the same holder information as well. Except for that F dimension. I'll change that back to 443 as well. Make sure it's 443. General page, let's say this is a back turn. And it's going to be tool number 2, or I can simply place this in the main gang in station 2, and it will change these numbers because that was one of the switch settings we had turned on it's one of the switch settings we turned on in the machine setup that forces the station to match up with the tool numbers. Now orientation. Now if it would be a back turn, I would want this orientation, 3V. And I'm going to leave this -1 inch to shift it out of the holder. And it's in station 2, and we hit OK. Now when I fire off simulation, take a look where it's sitting at. You see where it's sitting? And that's not going to work. And that's because what happens is it uses that same tool point, this same gauge point here, and simply when you change an insert to a different side, it basically rotates it around. So in other words, it's not using that same, it's using this point right here on the tip of the insert relative to this corner of the holder. So this is where we're going to need to shift the tool. So we'll go in and we'll edit that tool, and we'll simply add some shifting in Z and in Y. Now what we're going to do is we're going to shift in Z minus the 443 and in Y minus the 0.443. That's going to shift that tool back into this station. You can see where it's located now into that station. Now the same can take place, same problem can happen if you decide in midstream to change the hand of tool. For example, my first tool is a right-handed tool. If I go in now and change this holder now to a left-handed holder, so clearly the insert's on the opposite side, if I fire off simulation, you'll see how that tool is now in the wrong position, because again, it's using the left-handed holder to position the tool point here, 1 inch down from this corner, and the holder goes off in this direction. So when you make a change like this, and you go in and you want to change from a left hand to a right hand, just understand that you most likely will need to make a shift in in this case the Y. I'll move it 443 thousandths and fire off simulation, and now it's back in its station. So you need to understand that as you place tools in stations, you need to know that you have to move those things around as needed. Okay. All right, good. Now, if you have other tools defined that you want to use, for example, let's say that I have say I've got some sort of another interesting scenario of a smaller tool that I want to work with. Let's say, for example, a mini turning tool. If you look down the bottom, I've got a mini turning tool here. And I can easily go in and simply move this to the main gang turret. Let me go in. It's going to have to move it. Main gang, station number 3. And what happens, it'll position in station 3. Now what this is using is one of the mini tools, mini turning, mini grooving, and mini boring tools. A little bit of a trick about these tools. These tools aren't nearly as intuitive as the regular turning inserts. For example, in this insert, if I change the IC, the edge length is going to update automatically. However, what you find is in these mini tools, what I've discovered is that that's not always the case. You need to actually model this and draw this shape out so you get the right values for when you have an IC size. You get the right value for the edge length, and of course the angle is subjective, but the edge length for certain, you've got to have that number correct, and that number is all going to be based upon the IC, and the IC does not update this value. Matter of fact, if I do a right-click System Default, it changes to a value of 437. And quite honestly, if you were to go in, cancel, pull it back up. If you were to go ahead and use that default, you'll get an error that'll tell you it can't. Matter of fact, I'll show you that. Default. Okay, fire off simulation. Error creating tool mini turning. Now, so anytime you see that error creating mini turning, or any of the mini tools, then that means that there's a math error in your tool definition. So that's why it's important that you actually physically model this out to make sure you identify this correctly if you wish to use those mini turning tools. And so now if I define that correctly, I get the right tool in the right place. Only change I need to make here is I want to shift this tool out that 1 inch as well. So I'd go in and shift my X value minus an inch, and there we have that. All right, good. All right. Let's grab another turning tool, and we'll just move it into there. Let's grab, I've got an 094 grooving tool. I'll move it, move to station 4. We go back up. There it is in station 4. Same's true here. You want to make certain that this A dimension makes sense relative to the B. If you type in a number here, it doesn't always mean that that number is going to be right relative to B. So you need to model this out and make sure that you draw this thing correctly to get the right values for A and B. Because same thing will happen if I just went into B and did a system default, it'll say 0.1 for B, and we'll see. You see how 0.1 is bigger than A. If I try to fire that off, I get an error for that groove tool. So, like I say, use a little caution. These tools are great if you wish to use them. It's just that you got to make sure that the numbers are right, and so don't trust the defaults that are in the fields for any of these mini tools. Confirm them yourself, plug them in right yourself, etc. All right, now that tool looks kind of goofy. Let's see what we have in here for the settings. Oh, 194. What station did I put that in? Station 4. All right, so what's going on with that? Well, it looks like we may have a setting wrong in our machine setup. Let's go take a quick look at station 1, 2, 3, 4. See what we have? A little typo. See how it says a positive number? Take a look when I fire off simulation. So you can see the graphic of this solid has nothing to do with where this tool is located at. This tool is located based upon the settings in the machine setup for those stations. So simple thing like a plus instead of a minus can make a world of difference. And let me check the others as while I'm at it. And they're all okay. Now if I go back and edit that tool, of course I'll want to stick it out an inch. By the way, I'll talk about this setting. Actually, this setting was in there. I'll talk about that in a moment. But what happens is with that tool, and here's that tool setting here. There's that mini grooving tool. What I found is with those mini grooving tools, depending upon the where you're going to touch off the tool at. In this case, I'm using a 4V orientation. What I had to do is actually allow for that 94 thousandths of the width of the insert, this A dimension. I had to allow for that in a tool shift. I'll turn it to 0 so you can see what I mean. You see when I do this, you see how that station is actually sticking into wireframes. You can see it's actually not in line with the other stations. There, you see how it's sticking in here? That's because what it does, it looks at that side of the insert and it uses that as the gauge. So you have to take that into consideration. And in my case, plug in minus the 94 thousandths to shift it. Now I'll have that in the right location. Now, of course, once these are identified in the right locations here, I can move these around. Like, for example, well, let's grab another tool. Let's grab a cutoff. Let's move it into station 5. And of course, if I fire off simulation, there it is in station 5. It's really not in the right length, so I'd want to adjust it some. I'd want to add in a -1. Now notice, by the way, it already has shifts in here. That's based upon the fact that we have the type of handed tool is requiring that shift, and the fact that we're doing a 3V instead of 4V orientation. So this tool already was compensated. If it wasn't, change those to 0. Fire off simulation. You'll see how that tool is actually sitting through the back of the part. So just got to remember that when you define these tools, depending upon the orientation here, depending upon the hand of tool here, you will most likely need to make adjustments in the shifts for the X, Y, and or Z. Now keep in mind these shift numbers here are equal to the width of our tool slot. So the 443 is a constant number. You won't have to be monkeying around with those numbers. All right. Now, and of course this cutoff tool is another one of those mini turning tools defined as a cutoff. And that's one of the style choices you have. You can either have it as a back turn tool, a front turn tool, or in my case, a cutoff tool. Now the next consideration, for turning at least, is that you might not want your cutoff tool way down here on this end of the gang turret, because when that tool has to be in position to do a cutoff, the sub spindle will be up and engaged with the part most likely. And the concern here is you might run into this tool post. So usually a very good practice is to put the cutoff like in station 1, for example. So what I might do is move a couple of tools and stations. For example, I might take and I might say, for example, I'll move this back turn tool. I'll move it to station number 6. And I'll move this down to station number 2. And I'll move this up to station number 1. Now all that moving around should have no bearing on how the tool looks, because I did not edit the tool stations to position this. Now this important point here is that there's two schools of thought, if you will, for adjusting how the tool is positioned inside of these tool post areas. One is the way I've shown you, which is to go in and edit the actual tool shift, which shifts that particular tool. You can, of course, accomplish the same thing by going into Machine Setup, Main Turret, and going into a station and actually making those same adjustments here. I could have put in -1, I could have put in -443. I can make those adjustments in the stations. The disadvantage of that method is that if you were to move a tool from one station to another, you're kind of in trouble. You're toast, because you'd have to go back into the station to make those changes. So if you edit the tool like I've done in this case, then as I move the tool from station to station, its relative location is already defined inside the tool definition, not inside the station. And so that allows me the freedom of being able to move these tools as needed. So the point here is that once you define the tool the first time and you do it right, you get the orientation the way you want it, you get it setting the right way in your station, you have the freedom to move these tools from one station to another. All right, so now we're ready to move on now to some of the milling stations on the main gang turret. All right, so now let's define some tools from stations 7 through 15. We'll start by going up and selecting a milling tool. Let's just select something simple. Let's just do a drill. And in this drill, I'll call it a tool ID. We'll call this tool name of milling tool. Something simple. Tool number, I'll worry about that in a minute. I'll say a 7. I'll put that in station and number 7. And let's now go across to the tool change section. Now, one of the things about tool changes you're going to find is that, and we'll talk about this more when we actually do a couple of projects. There'll be times when you'll want to actually control this independently with each tool. You may have tools that you might not want to go home for tool changes, because, for example, on the gang turret, really on any tools, there are no tool changers. So this is something that's subjective and something we'll talk about a little bit more. Now, the turret name, this is going to go in the main gang turret. That's going to go in station 7. And now we need to talk about axis orientation. This is very important. What the axis orientation does is it orients the tool in the holder. Now, the key settings for you on this particular machine, is going to be on the main gang turret, stations 7 through 10. Those are those stations that are located next to the turning tools. Those will all use a X plus orientation. The only time you'd ever deviate from this is if you had a right-angled head. Otherwise, they're going to be X plus. Now, stations 11 through 15 can use either Z plus or Z minus, depending upon which direction they are pointing. We'll talk about that a little more as we move along. The rest, and also the same is true with this Z plus. This will get used in the end gang for stations 31 through 34. And the Z minus will get used on the sub turret. And more on that in a moment. Let's go in here. Let's define a holder diameter. Let's say it's 1 inch holder diameter, and let's say overall length of 2 inches, and the tool length is 1 inch. And I'll leave the defaults there, 1/2 inch. I'll make it a little smaller. I don't want a great big old tool. Say 1/4 inch in mill. Now it's 1/4 inch drill, excuse me. 1/4 inch, 118 degrees, fine. Cutting length of 1 inch is fine, and we hit our OK button. That's going to place this tool in station number 7, which should be sitting like so. Now notice what's happened in station 7 is that tool is actually sticking out of the location here. And that has to do with a little bit of a difference in how we define these stations. Let's do a stop here. Let's go ahead and take a look at that station. Let's go into station number 7, and you see we have a Y dimension to the center of the station, offset in X, and then but the tool is actually working off the holder base. And so what it's doing is it's adding a holder base here. Let's try a tool base to see what we get if we do a tool base this time. There. Now you see the tool base locates the tool up against this this position here. Now the station's a little bit big, so I will stop that and I'll make the tool holder a little bit smaller. Say it's 750, something like that. Okay, so there's that tool sitting in that station. and its location is it's off center, just like we had before. You kind of see how it's off center, but it's in the center of that station because unlike the turning tools where you might move these stations around, you don't want to be moving these stations around. The only thing you ever want to be adjusting here are going to be your lengths. For example, if I want this tool to be longer, I want the tool holder to be longer, which I'll identify it that way as a tool base. Or if I want the tool itself to be longer, I might go in and say, let's make this 2.5 inches long. I'll have a longer tool sticking out this way. I actually adjust everything when I did that. But so you see how you can make those kinds of changes. All right. Now, of course, from here, I can move this tool. I could copy it to any of the other 3 vertical stations. And if I just do a right-click, copy to station number, let's say 9, for example, fire off simulation, you'll see that tool sitting here. It's in the wrong position. That's because we made that adjustment to the tool station on 7, 8, and 9. Let's go back in. 7 should be tool base. Let's make 8 tool base also. Let's make 9 tool base and 10 tool base. Now let's fire this off again. There. Now you see that tool sitting here. Now I want to take that same tool and I want to put it in these stations out here. Now I can copy this tool into, say, station 11, which is the first of those stations. I can just do a right-click, copy to, in gang, station 11. Okay? But the big difference here is I've got to make certain that my orientation is right. If I don't, the tool is going to still be sitting vertically. You can't see the tool, can you? Go to wireframe. There it is. See, it's sitting inside because it's using the same orientation as these tools. Not good. So we change that and we tell it that this tool orientation is, in this case, the axis orientation is now Z-. And that's going to get the tool pointing in the right direction, like so. Now what we can do is we can take that same tool. Let's say we want to put it on the back side here. Well, in that case, we would copy it into the same station, main gang, into station number 11. But yet, in station number 11, we would change the tool orientation to a Z+. You see, get it pointing in the right direction. And we do an OK. We fire off simulation, and we now see it going in both directions. Good. Now, I want to place one of the tools out here on these stations. So I can take, for example, tool 11, which is pointing in the right direction. I can copy it to station number, let's say 21, end gang, station number, let's say 23. Let's put it on the end. And fire off simulation. Now I see that tool sitting here. So you see how this orientation is the same as this orientation, which is called Z- orientation. Which means it's pointing towards the Z- of our Z-axis. Now if I want to put a tool over here in this station, milling-wise, I could take this tool and copy it over there because that's going to be the same orientation. If I take the second tool on station 11 and I say copy to, end gang, let's say station 33. Fire off simulation. There it is sitting in station 33. That's a little longer because of where the tool base is located at, but that's fine. That gives us the location of where that's going to be in that station. Let's move this tool up a station. I'll move it up to the sub, up to station 21. Now let's add another tool. I've got a backbore tool. Let's put this backbore tool into, let's put it into 31. Actually, it should be into 23, so I'll move it to. Move it to sub turret 23. So moved it into 23. Now this tool is another standard insert type tool. It's a back turn tool. Actually, that's probably not the tool I wanted. Let me move that back out of there. Actually, what I wanted to put there is this mini boring tool. I want to talk about mini boring tools. So I'm going to move it into sub turret station 23. You can't see this on the screen, but I'm moving it to station 23. Now, this mini boring tool, just like before, you got to make sure these numbers match up. These numbers have got to be right. When I say 30 degrees, angle 1, angle 2, I've got to get my radius. All these numbers need to match up. Same with the holder. You've got to plug in numbers that work. This A dimension has to be bigger than this dimension. This FH dimension has to make sense. So it's real important to plug in those numbers accordingly. Now what that does is gives me this mini tool over here in this station that I could use for turning purposes. So I can use that little mini insert right there to come in and do a bore. I could use it with the sub turret to bore out something over here on the main spindle. Now another common practice is to, once we position the tool into the sub spindle here, we might have some additional turning to take place, and the only station we can use for that for turning is these stations here. And this station right here is a fixed turning station. There's a fixed station which you can use for turning. And so what I'll use is I'll take this back turn tool and I'll simply copy it. I'll move it to the end gang station 31. That puts it here in this back turn station, which basically places that tool there. Now, only problem is I've got, actually that's not the right tool, is it? Back bore is what I want. Can't remember the tools I'm using. Okay, let's try to move that back, unassign. Let's do that back bore. I think that's the right one. Move to end gang 31. Yeah. So here we have a boring bar sticking in here that we could then use we could use it to face, we could use it to turn, we could even use it to do a little bit of ID work on the sub spindle side once we transfer the part over to the sub. So now we've placed a few of the tools in their locations, and it gives you an idea or a feel for how those tools might be oriented. Alright, so now once we're at this point, we're really done with talking about how those tools are going to be adjusted, modified, tweaked, etc. And again, you can be a little bit fancier if you want to make sure this diameter of this tool is right. You can go in and change, looking at the tool station, you could go in and change this to be the right diameter holder, so you actually will see it correct size-wise. All those things are adjustments that you can make. The key thing is getting the direction of the tools pointing the right direction when they go in the stations, and then for the turning tools in this main gang, making any adjustments that are based upon the hand of tool and the orientation, 3V, 4V type orientation choices. All right, so now we are in this case finished with this machine setup, and you will find that there is another machine setup that's complete that have all these tools already defined. Of course, you can play around with these other tools, moving them into stations, kind of getting a feel for how those tools work in the different stations to understand that a little bit better. We're done with this exercise, and we're ready now to actually use this machine setup with the tools as we've defined them in locations in the locations in the machine. And then we're going to come in and we're going to machine a part using these tools and this machine setup and do an actual Swiss project.